In this paper, we propose the new dataset for photometric stereo, containing shapes with planar surfaces and rich details. Photometric stereo aims to recovering surface normal from a stack of images taken with a single camera and varying illuminations. Given these images and the light directions as input, photometric stereo reconstructs the surface normals of the object, where a surface normal n is a unit vector that is perpendicular to the tangent plane of the surface. Compared to other 3D reconstruction methods such as MVS, photometric stereo can recover single-view detailed shape. Here, detail recovery is the key strength of photometric stereo. However, this powerful capability in detail recovery finds no place in the existing photometric stereo datasets, which rarely contains fine detailed geometry structure. In addition, existing real-world dataset does not include flattened or near-planar surfaces, though they actually widely exist in our daily life. To address these two problems, we established the new dataset, DiLiGenT-Pi, which contains near-planar surfaces with rich geometric details. This dataset consists of 30 shapes and can be divided into 4 material groups: 10 metallic, 10 specular, 5 rough, and 5 translucent. To capture images, we constructed a capture system, which is a blackout cage without environmental lighting. To enable flexible illumination control, we integrate a 2-axis rotation platform. A single light source is positioned at the tip of rotation arm with a convex lens placed in front to provide parallel illumination. The object is put on the center of rotation system, surrounded by 6 mirror balls to calibrate the light direction. An industrial camera with a 50mm lens is equipped at the top. We select 10 representative calibrated and 6 uncalibrated methods to evaluate on the proposed dataset. The benchmark results are shown using mean angular error as the unit. The x-axis covers 30 objects and the y-axis displays 16 methods. Blue shades indicate lower errors, while red shades indicate higher errors. The 5 rightmost columns display the average errors, the first 4 for each material group, and the last one for the overall average. Let's first focus on these 5 learning-based calibrated methods. 3 of them give the best performance. Let's delve deeper into the details. CNPS is a per-pixel method, which calculates the surface normal pixel by pixel. In contrast, PSFCN is an all-pixel method, which gives the estimated normal as a whole. The results are slightly more blurred, which is possibly due to the spatial smoothness brought by the fully convolutional networks. Norm-attention PSN is also an all-pixel method, attaining results comparative to CNPS, but leveraging attention-weighted loss. We summarize the analysis above as the observation 1. Now, let's focus on the uncalibrated methods. The errors are much worse than those of calibrated methods. As we can see, compared to the ground truth, the estimated results are more colorful, indicating there is more variation along the axis direction. We fine-tune the selected uncalibrated methods, UPSFCN and SDPSNet, on our synthetic dataset, PS Relief, which consists of near-planar surfaces. On DiLiGenT dataset, the estimated normal predicted by fine-tuning model becomes much more flattened. The same fine-tuning process on the calibrated photometric stereo setting shows only a marginal flattening effect. This indicates that uncalibrated methods are much more sensitive compared to the calibrated methods. We summarize the analysis above as observation 2. Finally, let's focus on the difference among 4 material groups. We conducted an ablation analysis to examine the influence of reflectance based on the same shape. It turns out that translucent and rough materials are more challenging, which is our third observation. All the evaluation results can be found in the supplementary materials for your reference. To summarize, this paper contributes to photometric stereo by the following 3 points. Thanks for your listening.